Well, you probably just type in like the usual characters. It's just like a different font. Isn't that how wingdings work?
I've never used it. My extent to seeing his wingdings. His justification is that he doesn't like when people are reading his notes over his shoulder, so he doesn't want people to understand. Oh, yes, actually.
Well, I guess I'm my own chairman. Okay. So last time we talked about CFTs. Today I'd like to enlarge the discussion a little bit, and I'll talk for a while about UV complete Qfts. So UV complete Qfts are Qfts without cutoff. So it means that with whatever cutoff that we might have had at intermediate stages when we were trying to define our theory, we sent it to infinity. So these are supposed to be nice objects, nice mathematical objects, idealized objects. And perhaps you might be wondering, so in physics we always have some sort of UV cutoff, so why should we bother necessarily to send it to infinity? Well, it's following the usual logic that if you know that your physics system lives near some idealized mathematical object, then you expect to make faster progress by first studying the idealized object and then going back to your original problem. So what are the examples? So what are the examples of the UV complete CFTs? So one example are G fixed points. So these are scale invariant theories. And from the realization group point of view, the G fixed points are ubiquitous, because you can start from any theory, you can flow to the infrared, and then chances are that you're going to end up in some fixed point. Perhaps you have to tune some parameters. Or you can start from some lattice model. You can start from some local lattice model, like a three-dimensional Ising model, and you can flow to the infrared. And so, in fact, the way we are going to argue in our lectures is that the way we are going to explain that conformal field theories are ubiquitous. We are going to try to argue that most of these G fixed points, which are a priori only scale invariant, are also conformally invariant. So we will have to argue that scale implies conformal, and to the extent that we'll be able to argue for that, we will explain why conformal field theories are also ubiquitous. So just to repeat again, so these G fixed points, they come in simple cases and more complicated cases. So simple cases, for example, you can take some free, or as sometimes we say, Gaussian free theories. For example, you can take free massless scalar, or massless fermion, or whatever. But you can also have non-Gaussian G fixed points, and the critical point of the three-dimensional Ising model and of any other lattice model that you can come up with will typically be non-Gaussian. So these are the G fixed points, which are examples of UV complete Qfts, because they, once you go to a fixed point, it's scale invariant, and as Tom said, scale invariant theory by definition has no cutoff. But you can also have non-scale invariant UV complete QFTs. And so how do you get those? Well, the way you get those is you start from the RG fixed point, and then you perturb it by some interaction. So you take, schematically, you take RG fixed point, and then you perturb it by some interaction. And as long as this interaction by which you're perturbing, as long as this operator, or maybe you can take a sum of perturbations, as long as these operators are relevant, or perhaps marginally relevant, we expect that such a procedure is going to define a UV complete QFT. So just to give some examples which fall under this category, so QCD falls into this category with some small technical modifications down here. You can take, say, phi to the fourth theory, so QCD, phi to the fourth theory in 3 dimensions also falls into this category. QED in 3 dimensions with fermions also falls into this category. And so now it's time to contrast the situation with some other theories that you will have here later in the school, which are effective QFTs. So these effective QFTs are necessarily involve in their definition some UV cutoff, and so they are not equal to the UV complete QFTs. So it doesn't mean that they are not interesting. They are interesting and they are physically important, but it's just not the ones that we are going to discuss in these lectures. And so just to give an example of effective QFTs, if you take QED in 4 dimensions, or if you take lambda phi to the fourth theory in 4 dimensions, then these theories are, as we usually define them, they're effective QFTs because of the Landau pole. And another example, which is also very physically important, is the theory of chiral Lagrangian. So low energy dynamics of pions in QCD is defined by chiral Lagrangian, and here you also have a UV cutoff. So these effective QFTs are physically important, but they are not as nice. They're not going to. We are not going to expect them to have all sorts of nice properties that we will have for UV complete QFTs. And so, so I will restrict to the UV complete QFTs. And by the way, we don't really mathematically know very well what these UV complete QFTs are. You know, mathematicians come up with all sorts of possible axiomatizations. You probably have heard about Weitman axioms, Osterwalder-Schroeder axioms. Then some people think about UV complete QFTs in terms of random distributions. So we don't really know what the full axioms are, but we try to come up with reasonable axioms, and we try to make physics and see what comes out. Okay. Another thing that I'm going to restrict myself to in the following is to local QFTs. So if you have never seen a non-local QFT, you might be wondering what the hell I'm talking about. But if you only dealt with Lagrangian theories, then maybe you are wondering. But in fact, non-local QFTs exist, and some of them are even important for physics. So just to give you a very stupid example of a non-local QFT, if you take a local QFT which lives in RD, and then you just restrict it, you decide that you're going to consider correlation functions of this local theory only on some d-1 dimensional subspace. Now somebody just hands you a set of correlation functions without telling you where they came from, but actually they came from a local d-dimensional theory restricted to a subspace. Well, if you examine this set of correlation functions, you will find that actually, well, it's a non-local quantum field theory. So this example is pretty stupid, you might say. So let me give you a less stupid example. So this is example 1. So example 2 is going to be a theory. It's going to be a scalar field and I'm going to write a quadratic action for the scalar field, which I'm going to write it in momentum space, and I'm going to choose my action in momentum space to have a non-integer power of p. So so if s is equal to 2, then this is just a free massless scalar field. If s is not equal to 2, then this is a non-local theory. And the way you see that it's non-local is very easy. You just rewrite this action in position space, and you see that in position space it looks like ddx, ddy up to some constant, phi of x, phi of y, x minus y to d minus 2. D plus s. So this is clearly a non-local theory. Now, if you are interested in statistical physics, and if you just happen to deal in statistical physics with some lattice model which happens to have long-range interactions, and such systems exist in nature, then you might have to introduce in your theory interactions of this form. Well, and then your theory will be non-local. So such objects exist. Such objects are, at some point in your life, you may have to come to grips with them. But today I'm going to restrict. I would like to avoid dealing with this kind of a bit exceptional situations, and I would like to restrict myself to local quantum field theories. But now I have to define what the local quantum field theory is, and since I'm doing this very general framework, axiomatic framework, I have to define my local quantum field theory without saying something like, oh, well, it's a theory which has a local Lagrangian. I don't want to restrict myself to any Lagrangians here. So I have to come up with some definition, and the only reasonable definition that I'm aware of, which is sufficiently general for my purposes, is the following. So I'm going to define that the theory is local. This is a definition. So QFT is local if it has local stress tensor. T mu. And so local stress tensor is an operator, is a local operator of my theory, which I'm going to assume to have the following properties. So it has to be conserved. So as usual, this is away from coincident points. Now, to simplify my life, I'm going to assume that it's symmetric. And very importantly, I'm going to assume that it generates translations. Now, so I'm going to explain in a second what it means that it generates translations. But what I would like to emphasize is that I don't know any good and satisfying way to argue that any theory of the kind I'm interested in has a local stress tensor. So if you look at textbooks, then the textbooks usually say, oh, well, you have a Lagrangian, then from the Lagrangian you apply Noether theorem, or maybe like your path integral, you have a path integral, the path integral measure is local, blah, blah, blah. Now, I don't want to restrict to theories which have a Lagrangian. I don't want to restrict to theories which necessarily come from some local path integral. I would like to have a framework which, for example, applies to a three-dimensional Ising model or to any lattice model of statistical mechanics. Now, if you have a lattice model of statistical mechanics, there is, yeah, your model might have local nearest neighbor couplings, but how to argue that this locality of nearest neighbor couplings will translate itself at the critical point into the existence of a stress tensor with these properties, I don't know of any satisfactory way to argue for that. That's another cheat. Sometimes people say, yeah, so the question is, why don't we couple it to the metric? That's another often occurred cheat. I mean, it's a cheat. It's not a cheat for Gaussian theories, so it's not a cheat for Lagrangian theories. For theories which are weakly coupled in the UV, then you can try to couple the theory to the metric. If you have a lattice theory, what does it mean to couple a lattice theory which is strongly coupled at the lattice scale to the metric? Nobody knows how to, say, take a three-dimensional Ising model and put it on a sphere. It's very easy to put a three-dimensional Ising on a torus or any other locally flat manifold, but what it means to put it on a sphere, or what it means to put it on a weakly curved manifold, this is, I don't know how to do this. So if you know a good answer, please tell me, but I'm just going to assume this. So okay, so this is an assumption, so we have to have some assumptions, and from this assumption, my main goal will be to show that scale implies conformal invariance. So I have to explain what I mean by saying that stress tensor generates translations. So here I'm going to introduce this trick, which already occurred in Xi's lectures. So I'm going to do the following thing. I'm going to consider various closed d-1 dimensional submanifolds of RD, which I will call surfaces. So these are d-1 dimensional codimension 1 submanifolds. And with each such submanifold, I'm going to associate something. So I'm going to call it Q nu of sigma, which is just an integral of the stress tensor over this surface. ds mu t mu nu. So because I'm assuming that the stress tensor is conserved, this object does not depend on the shape of the surface. So I can change the shape of the surface as long as it doesn't cross any local operator insertions, and this object doesn't change. And so the way we call such objects, so she called it conserved charge, and this generated some confusion in the audience. So I'm going to call it topological surface operator. So if I have any correlation function of operators phi1 of x1 and so on, and if inside this correlation function I insert this guy q nu of sigma, then this is invariant under small deformations of sigma. So let me write it phi1 x1 q nu of sigma prime. Okay. I'm only working in Euclidean space.
Could you repeat the comment?
So the question is, the comment was that I'm not assuming the metric. I'm assuming the metric. I'm working in a flat Euclidean d-dimensional metric. So this follows from the definition of the conservation of the stress tensor, but now I'm going to play the usual trick. So I have a, I'm going to take sigma surrounding all of my operator insertions, and then in the left-hand side I'm going to take this sigma and send it to infinity. So I'm going to take it as a, for example, a sphere which goes all the way to infinity. The radius of this surface goes to infinity. While on the right-hand side, I'm going to shrink this sigma, and I'm going to surround every. So I'm going to shrink it. I'm going to split it into several small spheres, and I'm going to surround each of these operators with this sphere. So I'm going to erase these links. So I'm going to erase them, and so, under some reasonable assumptions that I'm going to discuss a bit later on, once I send this sphere to infinity, the left-hand side goes to 0. And so I'm just left to determine the right-hand side. And so I get this equation that 0 is equal to the sum over I phi1 of x1 dot dot dot, and then for the term that I'm surrounding, so I have this thing which I denoted q nu times phi I at the point xi dot dot dot. You have this, and so here I introduce this definition that I call q nu times phi at the point x as a limit when sigma goes to x of this operator that with which I'm surrounding, ds mu t mu nu of x. Let me call it phi of xi sigma. So in fact, since I'm assuming that since this is a topological surface operator, I don't really have to take the limit. This quantity is independent of the size of sigma, as long as this sigma does not include any other operators. But the fact that I can take this limit, it tells me something very interesting. It tells me that this object, so I had an object phi in my theory, I defined a new object which I called q nu times phi, and this object, since I can shrink this surface sigma, I can take it as small as I wish, it's also going to be a local operator. That's as much as I know so far. And so now I'm going to state it as an assumption. So what do I mean by this? By this phrase that T mu nu generates translations. So by this I mean that q nu times phi of x equals d mu phi of x for any phi. That's my assumption. So in other words, q nu is equal p nu, the generation of translations. So okay, so this is my assumption. I think it's a pretty minimal assumption. And now you can perhaps guess what's going to happen. So you see, last time we finished the lecture by writing down some infinitesimal version of what we mean by correlation functions being invariant under conformal transformations. And so this infinitesimal version involved a bunch of objects Q acting on local operators. And these objects Q, they were satisfying conformal algebra. So now we don't have all of these Qs at the moment, but we only have one Q, namely the one which corresponds to the stress corresponds to the translation. And so what we are going now to do is we are going to, using the fact that this Q exists and it generates the translations, we are going to generate more Qs. And little by little, by adding some extra assumptions, we will build up to the full conformal algebra. So that's the idea. Okay. So now we are launching into this into the proof of this theorem that scale implies conformal, and but for the moment I'm going to stay with I'm not going to assume scale invariance for the moment. I'm going to stay in the framework of the general Poincare invariant quantum field theory. And the first thing I'm going to do is that, okay, here I assume the existence of the translation generator as a surface operator. I'm going to try to construct, to begin with, the rotation generators. That's going to be my first task. And even before I'm doing this, I am going to try, let us first of all understand, so this thing that I assumed, that Q nu times phi equals d mu phi, I would like you, now, of course, if you know anything about quantum field theory, this is not surprising at all, but I would like you to pause for a second and realize how amazing this property is, and it's kind of miraculous that it holds. And to convince you that it's miraculous, I would like to explain what this property means for the correlation functions of t and phi. So you see, how on earth are we going to have that this limit, when we take this t mu nu of x and we integrate it around a very small surface around xi, how on earth is this always going to come out equal to d mu phi of xi? So let us think for a second how is this at all possible. And the only way, I claim that the only way this is possible, I can imagine this to be possible, is if we have the following OPE. So t mu nu of x, the correlation function of t mu nu of x near any local operator phi of 0. So if I take x close to 0, this insertion, so I'm assuming that there are some other insertions but they're far away, this is going to be, of course, singular. And among all possible singular terms that this OPE will have, so there are going to be a bunch of singular terms, but then there has to be a term which is going to look like this, b mu nu lambda phi, it depends on phi, of x d lambda phi of 0. So this OP might contain more singular terms, it might contain less singular terms, and this particular term b mu nu lambda x d lambda phi, when integrated around surface sigma, it should give me d mu phi. So what does this mean? Okay, it means let us suppose that the surface sigma is very, very small. Then the volume of the surface is, well, let me just write down. So it means that I have to have this property that integral b mu nu lambda phi of x over any sigma, it has to be equal delta mu nu. So that's first of all what I have to have. No, sorry, it has to be equal delta nu lambda. So if this property holds, then when I integrate t mu nu, I'm going to recover d mu phi. Sorry, here it has to be d mu phi. Okay? So in particular, this means, so since the volume, since I take this radius, if I take this radius of the sphere very small, the volume scales like x to the d minus 1. So it means that this function b, I don't know what this function is. I mean, it might be very complicated. It might have complicated tensor dependence because it might depend on x mu, on all other invariant tensors. But leaving this tensor dependence aside, I should have that this function b should scale for small x as 1 over x d minus 1. So this tells us something interesting. So this tells us that just by comparing dimensions of terms in this OP, so we have phi here, we have phi here, we have one derivative, and here we have 1 over x d minus 1. So this implies that in a scale invariant theory, the scaling dimension of the stress tensor has to be equal to d, just from here. And okay, if our theory is not scale invariant, but UV complete, as we said, such theories, they arise from some fixed point at short distances, UV fixed point. So then it will be the scaling dimension of the stress tensor at the UV fixed point. Okay. So next step, we would like to construct, we have one topological surface operator which generates translations. We would like to construct more topological surface operators, more TSOs. And the way I'm going to construct them, I'm going to take some vector field epsilon of x, and I'm going to construct an object q epsilon of sigma by now integrating t mu nu of x, epsilon nu of x over the surface sigma. So this is not going to be a topological surface operator for any vector field, but it is going to be if this object is conserved. So if I require that d mu, t mu nu epsilon nu is 0, then we are going to get TSO. So this condition, since the stress tensor is conserved, this condition is equivalent to t mu nu d mu epsilon nu equals 0. And since the stress tensor is assumed symmetric, this is going to be satisfied if d mu epsilon nu plus d nu epsilon mu equals 0, which is the killing equation. So last time we had conformal killing equation for conformal transformations. Now we're just dealing with Poincaré. So we have this killing equation, and this killing equation is solved by only two vector fields. It's solved either by epsilon equals const or epsilon mu equals omega mu lambda x lambda, which is the rotation vector field. But okay, later on we are going to make further assumptions like scale invariance, and so we'll have more more vector fields which give rise to TSOs. But for the moment we have to work just with these two. And now we can recycle a bunch of our discussion. For example, this argument here, this argument about taking a surface, deforming to infinity, deforming to small surfaces, and so on, clearly it works for any topological surface operator, as long as I can push this thing to infinity and argue that this contribution goes to 0. So for any TSO of this type, I have the equation that sum over I phi 1 x1 dot 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 q epsilon acting on phi I at the point xi dot 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 equals to 0. So you can make an argument, you can try to understand why you can drop this term at infinity. It's not actually hard, because you see, when you send this term to infinity, what are the possible sources for the growth? So if you send this term to infinity, of course the volume of the manifold grows as r to the d minus 1. Then your vector field epsilon might also grow at infinity. For example, here epsilon grows as x, and if you consider special conformal transformations, epsilon is going to grow as x squared. So this gives you some source of growth. But also you have the stress tensor here. And the stress tensor, as we discussed, is an object of dimension d. So it means that correlators of the stress tensor are going to go as 1 over distance to the power 2d. And so now you have to think whether, who wins. Is it the stress tensor wins or is the volume wins? And you can convince yourself for the vector fields that we are going to be interested in, which are the conformal killing eventually, it's always the stress tensor wins, so that contribution always goes to 0. So you can drop it. Okay. Any questions? So now, okay, in this very general framework, we have this vector field, we have this q epsilon, we define it as an integral of the stress tensor. Now, what is going to be the physical meaning of these q epsilons? We would like that these q epsilons have the same physical meaning as in our first lecture, namely that they correspond to spatial transformations corresponding to this vector field epsilon. So how can we see this? So for the translations, for the rigid translations, this was our assumption. But now we are no longer considering rigid translations. We are considering more general vector fields. So how can we argue that this q epsilon is still a spatial transformation? Well, actually, it's not hard at all to argue for that, and the reason is, so let us argue. So I would like to argue that any q epsilon times phi of xi, it will contain a term, so it will have the following form. D mu epsilon, no sorry, it will contain the following term. Epsilon of x times d mu phi, there's always going to be this term, proportional to epsilon times epsilon mu times d mu. Plus, there might be further terms which I cannot predict in general, so they will depend on epsilon, and they involve, so these further terms, they will involve derivatives of epsilon. And so since, as I'm going to argue in a second, there's always this term, epsilon mu d mu phi, in any q epsilon, that's why I'm going to claim that this q epsilon has a physical meaning of a spatial transformation. And what is going to be the meaning of these other terms? Well, that's also easy to understand. So we know that sometimes when you do the spatial transformation, you also have to do maybe a rotation or maybe a scale transformation, but that depends on properties of your fields. But this term is always there. So how are we going to argue for that? Well, it's very easy. So this is our q epsilon. Q epsilon is given by the integral t mu nu times epsilon nu of x. Epsilon nu of x, for the translations, it was just a constant. Now it's some x-dependent vector field. But let me expand it in a Taylor series around the point where the operator phi is inserted. So they're going to be the first term in the Taylor series, which is just a constant, and it's exactly, so the contribution of this constant term is going to be exactly the same as the contribution for the p nu. So it's going to give me this. It's going to come from this term b mu nu lambda in the OPE. Now, if I take further terms in the Taylor expansion, so they of course come with powers of x, and they multiply these derivatives. So okay, here I wrote d epsilon, but in fact it might be different. It's not necessarily a contracted derivative. D mu epsilon nu. But I have those more singular terms in the OP that I haven't written down. So here there are more singular terms. The term b mu nu lambda, it will not give a contribution for the subleading terms because it had just the right scaling to give a non-zero contribution for a constant. But the more singular terms that I have not written down, and okay, they are more complicated to write down, and they are non-generic, they depend on phi. So those more singular terms, they have a chance to contribute, and if they are there, if they contribute, they will give rise to these extra terms which are going to be proportional to the derivatives of epsilon. So this is the structure, and we can understand it in a completely general way. Okay. Any questions? So far so good. Now I'm going to do this. I'm going to. So I need some space. This can erase. So this was pretty general for any possible TSO we might have in the future. But for the moment, we are just doing with Poincaré theory. So we have just one TSO, one more TSO at our disposal, which is the one corresponding to the epsilon nu equals omega nu lambda x lambda. So let us apply this logic to this TSO. And in addition, I would like to take this TSO and I would like to act on T mu nu itself. You see, here I was discussing what's going to happen if Q epsilon acts on any phi, but now I'm going to act on T mu nu itself, and I would like to understand what's going to happen. Well, what's going to happen? First of all, as I discussed, I'm always going to have this term epsilon rho d rho T mu nu. This is the term that this is the generic term which is always there, the completely general term which is always there. Plus I will have terms which are proportional. Here I will have some more terms, and these terms are proportional to d epsilon, and d epsilon is omega nu lambda. So I will have terms which have to be proportional to omega. So which terms can I write down? I can write down, so they have to be linear, of course. And so the only terms that I can write down, so here is going to be some magic. So the only two terms that I'm going to write down, which I can write down, are C1 omega mu rho T rho nu plus C2 omega nu rho T rho mu. So these are really the only terms that I can write down which are linear in omega and which are which respect the dimensions of our equation. So T mu nu had dimension delta equal d. So here I have to have also terms which have dimension d. So generically the stress tensor is going to be the only dimension d operator. So that's basically the only thing that I can have. Of course, this is very general, but now I'm going to fix this coefficients C1 and C2. The first thing I'm going to say is that, look, the whole thing has to be symmetric under the interchange of mu and nu. And this means that C1 has to be equal to C2. Okay, lo and behold, this is the same coefficient. The second thing I'm going to require is that, okay, I leave you as an exercise that the stress tensor is conserved. So the left-hand side of this equation is conserved if I differentiate in x. But the right-hand side, okay, here, epsilon is an x-dependent quantity, so it's not manifest that this right-hand side is conserved. But if you impose conservation, then I claim that you can fix this coefficient c and it's equal to -1. So once the dust settles, with this very general argument, we actually proved that the following equation is true. Okay. So next step, I now have two q epsilons. I have q epsilon corresponding to the rigid translation and I have q epsilon corresponding to the rotation. And I know how both of these q epsilons act on the stress tensor. Okay, here I just wrote it in a form adapted to the rotation generator, sorry. But now I'm going to take the two equations and I'm going to write them in the form which is compatible with both of the Killing vectors. So I'm going to write the following general formula: q epsilon T mu nu equals epsilon rho d rho T mu nu, and here minus d rho epsilon mu T rho nu plus d nu epsilon rho T rho mu. So I claim, and you can very easily check, that in this form, written in this form, this equation applies both for epsilon equals a constant and for epsilon equals omega times x. So what do I do next? Well, I guess it should be pretty clear from Xi's lecture yesterday. I'm going to derive the algebra. So as it was explained yesterday, in the two-dimensional CFT, we have this very nice trick how to compute commutation relations of the Virasoro generators. And one nice thing that maybe is not sufficiently emphasized is that the same trick also works in d-dimensional CFT. So it's not specific to two dimensions. So the way it works is as follows. We take two surfaces. So we have a surface sigma 2, and then we surround it with some other surface sigma 1. So we have two operators, q epsilon 1 associated with the surface sigma 1, and q epsilon 2 associated with the surface sigma 2. And so now we would like to compute the commutator of these two topological surface operators. So when we compute the commutator, it means that we have to take the difference between this contribution and another contribution where this charge q epsilon 1 sigma 1 is inserted on this other surface, let me call it sigma 1 tilde, which is now inside sigma 2. Now we pick some point here t mu, where t mu of x sits, and now we deform these two surfaces sigma 1 tilde and sigma 1 so that they surround this insertion. And the result of what happens when we take t mu and we surround it with this topological surface operator is precisely given by this equation that we already derived, that how q epsilon x on t mu. So now when you integrate out this equation over the surface sigma 2, you get a commutator, right? So that's a calculation that that I invite you to do. And once you do it, you get the following formula, that the commutator of q epsilon 1 and q epsilon 2 is given by q minus the Lie bracket of epsilon 1 and epsilon 2. So the Lie bracket is, just to remind you, epsilon 1 epsilon 2 is equal to epsilon 1 d epsilon 2 minus epsilon 2 d epsilon 1. So this is the calculation that I invite you to do as an exercise. In the lecture notes you will find some hints how to go around doing it. So it's a bit less straightforward than in two-dimensional CFT, because in two-dimensional CFT, when you do it for the stress tensor, you just have these contour integrals of holomorphic functions, so you just pick up poles. So here you have to do with this, there is danger of getting lost in the indices, so you have to think a little bit how to organize this computation. And I give some hints, but in the end, once the dust settles, you get exactly this. And now this formula written in terms of commutators of vector fields is precisely the one that gives you that. So this formula is equivalent to Poincaré algebra. So lo and behold, we reproduce the Poincaré algebra in this formalism. Now you can think that this was all very masochistic because it's just Poincaré algebra. Of course, we know that we have Poincaré algebra, but why did I have to work so hard, introduce these topological surface operators, these commutators, this? It's one thing if you have to do it for Virasoro, then you feel like you're doing something non-trivial. But why here? The answer is that now, okay, we worked pretty hard for the Poincare algebra, but now we will just breeze and generalize it to the scale invariant case and conformal case with basically zero extra work. So this is the advantage. So now that you mastered this formalism in a simple setting, and now we'll generalize it to the interesting setting. Any questions? Yeah.
Am I thinking about this right? Does translation invariance apply rotational invariance?
Not really, because I assumed that my stress tensor was. So the question was, did I just derive that rotation invariance implies translation invariance, or the other way around? Translation implies rotation. Well, not really, because I included in my list of assumptions that the stress tensor was symmetric. So this allowed me to construct this extra topological surface operator. If I did not have this assumption, then I would just be stuck with translation invariance, and with no extra topological surface operators, I would not be able to prove rotation invariance. However, what I did not have to assume, and that's nice, that rotations act correctly on the stress tensor. So what I was able to show in this rather economical treatment is that by having that translations act correctly on the stress tensor, I was able to show that rotations generators also act correctly. So this was somewhat more economical. Any other questions? Yeah? No, not really. I mean, this. Yeah. So the question was if I'm assuming some sort of radial quantization, because I'm talking about commutators. No, I'm not assuming radial quantization at the moment. What I have here is that, okay, I have a set of local operators of my theory, and I have the vector fields which form a finite dimensional algebra, which act on my space of local operators. So I'm just saying that this representation is actually a representation of the Poincare group. So what I just proved is that local operators transform in representations of the Poincare group.
Somehow, you had those two contours. One was at the larger edges than the other, and then you are changing the order and interpreting it as
So the question was, since I have these contours and since I change the order, it looks like I'm assuming some sort of radial quantization. Well, I'm not, because these contours are just definitions, they're just insertions in the path integral. They don't even have to be spheres, they can be like cubes. In fact, when you do this exercise, you better choose the contour as a cube. But it doesn't mean that I'm assuming cubic quantization or anything. So later in this course, I'm going to talk about quantization in detail and so on, and there it will become hopefully more clear what is the relation between the two pictures. Right now I'm just saying, okay, I have a bunch of local operators and I have a machine. These Qfts are just a crank, which allows me to start with some local operators and produce more local operators by acting with Qepsilon. And to turn the crank, I don't need to know anything about Hilbert space or anything about any sort of quantization. All I need to know are correlation functions. So if I know correlation functions of phis and I know correlation functions of T mu's at non-coincident points, I can integrate the T mu correlation functions and I can generate out of phis new local operators. So this is a very economical point of view, which is, by the way, exactly the same as in two-dimensional CFT. So there are 2 points of view on quantum field theory. One which is kind of correlation function point of view, and the other is a operatorial point of view. And so far, I'm only doing correlation function point of view. Any other questions?
So in Xi's lectures, he derived there will be How do you think about the OP here?
So the question was, how should we think about this OPE? Am I already assuming some sort of state operator map and so on and so forth? So I'm, compared to Xi's lectures. So this OPE, so there are two forms of OPE. One very strong form of OPE is valid in conformal field theories, which is a convergent OPE. So if I include an infinite series, then as we will see also in my lectures, the OPE is just convergent. It's a convergent expansion in some Hilbert space, blah, 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 very powerful. Then there is a weaker form of OPE, which is true in any UV-complete quantum field theory, which just says that correlation functions at small separations, they have an asymptotic expansion. It doesn't have to be convergent, but there is a certain asymptotic expansion. So here I'm using the OPE in this much weaker form for the moment. So I am assuming that that when I'm inserting T mu of x near phi, then there should be this asymptotic expansion of this form. And well, if you wish, yeah, this is an extra assumption, but that's, I mean, I'm hard pressed to think how this equation could be true if this were not true. So yeah, this is an extra assumption. Okay, so now we are ready for the big shot, for scale implies conformal. So far I was talking about Poincaré invariant theories. Now let me specialize to scale invariant theories. What's a scale invariant theory? It means that in addition to the vector fields that I discussed, I expect to find an extra TSO which corresponds to the dilatation vector field. Which is this one. So I now have to go to my definition of TSO over there. So the TSO is going to be given by exactly the same formula as before, by this formula. But now I would like to impose the condition that this operator is conserved. And since epsilon mu is equal x mu, so this is for the dilatation generator, this is equal delta mu for epsilon d. So I see that this TSO is going to be a TSO if T mu is equal to 0. Okay. But now, once I have this condition that T mu is equal to 0, I realize, very luckily, that I can construct more TSOs. So from here I get more TSOs, namely any conformal killing vector field gives me a TSO. Because if T mu is equal to 0, so conformal killing means d mu epsilon nu plus d nu epsilon mu is proportional to delta mu times some function, c of x. And so the fact that it's proportional to some function is going to be enough to make that T mu nu d mu epsilon nu vanish. So any such conformal killing vector field, in particular the special conformal generator vector field, is going to give rise to a TSO. Yes?
How does this fail in Maxwell Theory in 3 dimensions?
I'm going to discuss caveats in a second. So there is some, there is some caveat down here. I'm lying to you a little bit, but let's forget about this for a second. So this caveat is not very important. So it's not shouldn't make you lose sleep. So okay, so this is basically this is the first step towards. Since I have now this extra TSOs corresponding to conformal killing vectors, this already means that I have conformal invariance. What is missing? There is something else to be shown. Namely, I would like to work out for you the conformal algebra. So what does this mean? So I have so we worked out the Poincare algebra here very nicely by using the fact that Q epsilon acting on T mu nu is given by this formula. And this formula we showed that it's valid for epsilon equals constant and for epsilon equals omega x. But now I have more TSOs, and so I have to have a more general formula. I have to have a more general formula which would be valid for all conformal killing vector fields. So what that formula is going to look like well, I'm not going to rewrite it, I'm just going to add an extra term. So if I would like to have a formula which would be valid for all conformal killing vector fields, then, okay, these terms that I already have, I cannot modify them. Their coefficients are already fixed. But there might be one more term which is of this form, plus d dot epsilon T mu nu. And in fact, the coefficient of this term can be fixed because we know that the stress tensor has dimension d. So this coefficient here is fixed by delta t equals d. And so I claim that now that I have a bunch of new TSOs, all the conformal killing TSOs, then this general formula is valid for any conformal killing epsilon. And so now that you have this more general formula, you go back here, you run this argument again with which is the cubic quantization argument. You deform the surfaces, and you have to show. I mean, it's actually a bit of a subtle argument because when you start doing these contour integrals and picking up terms, you realize that here there are a couple of terms which are proportional to t, and those terms they just give you the Lie bracket of vector field spot on. But then there are some terms which are proportional to the d rho T mu nu. So these terms are weird because all these topological surface operators that we are considering, they are given as integrals of T mu nu, not of integrals of the derivatives of T mu nu. While here in the right hand side you have the derivative of T mu nu. So you have to show that these guys cancel, and this requires some integration by parts, and that's why it's good to use sigma being a cube to do this computation. So let us recap. What did we do? In first lecture we introduced conformal group, and first of all we introduced this as a group of transformations acting on space, transformations of space. Then, conformal algebra. Then we took the same algebra and we postulated that that algebra was acting on the space of local operators. That was postulated, that was not derived. So today's construction, where we assume the stress tensor and we introduce the topological surface operators, and these topological surface operators acting on local operators, and eventually when we derive this equation for the commutation relation, it proves in this additional setting what in the first lecture we postulated. So that's nice. So why is it nice? Because the fact that the algebra acting on local operators is the same as algebra of special transformations, you might think that this is not totally obvious. For example, you have seen that in the two-dimensional CFT, you have an algebra of vector fields, of holomorphic vector fields, which are the spatial transformations. But the algebra acting on the local operators is not the same as the algebra of vector fields, but it's a deformation thereof by the central term. So here we have shown that nothing like that happens in d dimensions. So in d dimensions there is no deformation. The algebra acting on local operators is exactly the same as algebra acting on in space. So you might think like, what is the difference here and so on, I have some comments about that in the notes, but basically it has to do something that with the fact that these epsilons, they're only quadratic in x, while holomorphic vector fields, they have any dependence on z. So in the remaining 3 minutes, I have to discuss the caveat. So in fact, I proved this theorem that scale implies conformal, but this theorem has counterexamples. In fact, there are some theories which are scale invariant, local, but not conformally invariant. And so how do they evade this theorem that I proved? So the culprit is this assumption that I made. So I lied to you when I said that scale invariance requires T mu mu equals 0. So this is generically true, but it's not always true. In fact, I could consider a more general condition that T mu mu is a total derivative of some object called virial current. And the theory would still be scale invariant. And to see that it would be still scale invariant, I have to construct this topological surface operator. So the logic of topological surface operator still remains. So I take epsilon being the dilatation vector field, and then I construct the following operator T mu nu epsilon dilatation nu, and here I add, just by hand, I add v nu minus v nu. So I construct, I modify the definition of the topological surface operator by this extra term v nu. Now you can see that thanks to this relation that the trace of T is the divergence of V, this object is still a TSO. And so I have a scale invariant theory. So it's a scale invariant theory, but is it a conformally invariant theory? Now it turns out that if this virial current, if it has a special form, if it by itself, if the virial current by itself is a total derivative, if I can write it as d sigma L mu sigma of some new object, new local operator L, then I can push this further and I can define also the conformal TSOs, the conformal killing TSOs, and the definition is going to be the following. So Q epsilon of sigma equals integral ds mu t mu nu epsilon nu minus v nu 1 over d epsilon plus L sigma nu 1 over d sigma d epsilon. So you can check that this definition of the TSO works for any conformal killing vector in d larger than 2 dimensions. But if V mu is not of this form, if I have a viral current, but I cannot represent it as a total derivative, then I'm screwed. Then my theory is scale invariant but not conformally invariant. So if this condition is not satisfied, so if V is not equal to dl, then I have scale without conformal. Yeah, to construct this extra TSOs. So the question was if I'm assuming any locality. Yeah, to construct this extra TSOs, I have to have that L is local. Otherwise, it's not going to work. And okay, yeah, is this possibility actually realized? So this looks a bit weird. Is this actually realized? Well, it is, and there is a very famous example of a theory which realizes this. This phenomenology, which is actually even physically relevant. So, and this example is theory of elasticity. So it's a Gaussian theory defined by the following action. It's just a vector field. And I have two coupling constants, alpha and beta, which are related to elasticity moduli of. So imagine a d-dimensional elastic body, and I have a deformation vector of this elastic body, which is this vector field u. And now I have two elastic moduli which correspond to how the energy, the deformation energy of the body depends on the deformation, alpha and beta. So in Euclidean signature, it's a totally reasonable and physically relevant theory. In Minkowski signature, it would not make sense because it would be like a vector field without gauge invariance. So it wouldn't be unitary, but in Euclidean signature, it's totally okay. And you can check that this theory actually has a viral current. So it's scale invariant because everything is there are no mass parameters. So this theory is, of course, scale invariant. You compute the stress tensor, and I give it as an exercise to show that this theory has a viral current, and the viral current is not a total derivative. So this theory is scale invariant without conformally invariant. So now that you know that there is this caveat, should we be worried? Well, we kind of think that this caveat cannot be very important because most, like by and large, all of the theories that, all of the fixed points we see are actually conformally invariant. So how come this caveat does not apply to them? Well, the reason is that this viral current is a pretty weird object, if you think about it. You see, the stress tensor has dimension d, the viral current has dimension d minus 1, so it's a vector operator which has dimension d minus 1, and yet it's not conserved, because if it is conserved, then the divergence is 0, then we are back to the usual situation. So now, in an interacting theory, we expect that all vector operators which are not conserved, they will pick up anomalous dimensions. And so basically in an interacting theory, we simply will not have any candidates for operators to appear in the right-hand side of this equation. And so for this reason, it is believed that interacting theories, they are not generally subject to this caveat. So while Gaussian theories, free theories, like for example the theory of elasticity, it's a free theory, they might. So that's so that caveat is something to keep in mind, but not to lose your sleep about.
We're 5 minutes over. So
Yeah. Actually, I am done. Yes.
So you see there's no way to deform this theory of elasticity to make it interacting and not conformal? Is the scale invariant but not conformal?
So the question is, what's going to happen with this theory of elasticity if we deform it and flow somewhere and will this infrared, and suppose that we reach some infrared fixed point, and what's going to happen with this infrared fixed point? Might it be conformal? I think generically it will be conformal for this argument. And in fact we know such cases, like because there's another example of scale invariant theory which is not conformal invariant, which is the Maxwell theory in 3D. But we know that if we take this Maxwell theory in 3D, we couple it to fermions, we set up an RG flow, and that RG flows somewhere and the infrared reaches a fixed point. There are fixed points of such theories, Maxwell coupled to fermions, and those fixed points are actually conformal. So the UV theory might be scale without conformal, and infrared theory may be actually conformal. So there's no contradiction here.
Is there an example, like another example of a theory that realizes conformal invariance in the latter way, where the theory of invariance is
So the question was, is there any example of conformal theories where you need to construct this conformal killing charges in this funny way with L's and V's? In most cases, when you have this this structure arising, V and L, you can actually redefine your stress tensor. So I did not define it, but this is a procedure which is called stress tensor improvement. You define an equivalent stress tensor which is actually traceless, and so you don't have to go through this song and dance. But there are some cases in 2 dimensions. So there are 2-dimensional local theories, Gaussian free theories, which are actually invariant only under SL2C, but not under the full Virasoro algebra. You might wonder, okay, how the hell can this happen? Well, this can happen through this mechanism, because if you have this conformal killing TSOs, this construction only works for vector fields which are up to quadratic order in X. So it's not going to give you it's not going to give you a holomorphic vector field TSOs. So if you have, there are theories in 2 dimensions where you have conformal killing TSOs of this form, but the stress tensor is not improvable. You cannot improve it and to get a traceless stress tensor, because if you could, then you would get full Virasoro. So such examples exist.
So the biharmonic scalar.
Yeah, totally right. So it's a biharmonic scalar.
let's meet back again at 2 o'clock for clay quarter.
Is there not a proof maybe in D equals 2 without counterexamples if you like add some assumptions or something? Maybe unitarity?